right, welcome back. Today, Chapter 3, Section 5.1, Unique Factorization. An important concept when we have it and when we don't. All right, to begin, remember that in an integral domain, the cancellation law works. So, if we have a non-zero a, and a times b is equal to a times c, then we can gather everything on one side, factor out the a, so that a times b minus c is 0. And since a is not 0, that means b minus c has to be 0. In other words, b is equal to c. So what that really means is it's as if we could have canceled out the a's over here to begin with. All right, let's do a little lemma here that we're going to just use a fair amount. This is all really trivial. All right, in the lemma, let's assume that D is an integral domain and A is in D and not 0. All right, number 1, if A divides B and B divides C, when at least B is non-zero, then of course A divides C. The next is that if A divides B and A divides C, then A divides any linear combination of B and C. All right, the proof of these is essentially exactly like we saw in Z. Let's just make a brief comment on part 3. All right, since A divides B, we get the following. But then since B divides A, we can also factor out that A. So we get this, B is equal to BDC. And now we can use that cancellation law. So we get 1 is equal to DC, and so therefore both C and D are units. Okay, so then going back to this original equation, C is a unit, move it to the other side, and we get our result. All right, one of the big properties we had about the integers was that Z had unique factorizations into irreducibles, that is, into primes. And it just seemed like this should always be true because it works so easily in the integers. People just assumed it was true. And it led to actually a number of false proofs for the Fermat's last theorem. And what people discovered was that, in fact, a lot of domains didn't have unique factorization. And so here's an example. All right, so one of the first examples you normally see of this is Z attached the negative square root of 5. So this would be the set of all a plus ib root 5s, where a and b are integers. This would be a subring of C. Now to see the problem here, let's introduce some terminology called the norm. All right, we'll define the norm of some z in this z attached negative square root of 5 be a squared plus 5b squared, where z is this a plus ib root 5. Now, if you check, this is actually just in the sense of complex numbers, z bar, and that's why it's called the norm, because over the complex numbers, that's the norm. Okay, what's trivial is to check is that the norm of a product is the product of the norms, and you probably already knew this for complex numbers, so it continues to hold here. So if we happen to have a unit in this ring, then the norm of u times the norm of u inverse, since it's multiplicative, that's the norm of 1, and by calculation, the norm of 1 is 1. Now, what you'll notice by this formula up here is that this norm is always integer valued. And so here I've got two integers that multiply to 1. It's also not only integer valued, but it's bigger than or equal to 0. So I have two non-negative integers that multiply to 1. Well, that can only happen if they were both 1 to start with. So as a result, if you have a unit, this norm always spits out a 1. All right, the converse is going to be true as well, that if the norm of something in this ring is 1, that's because it was a unit. So suppose z is in this ring and the norm is 1. Well, by definition, z times z bar is the norm of z, which is 1. So that means I found an inverse to z. namely z bar. So something in this ring is a unit if and only if its norm is 1. In other words, just wrote that out. The units are all the guys who have norm 1. Well, what does this mean? It's all the a plus ib root 5s. The a's and b's have to be integers. And the norm being 1 means a squared plus 5b squared is 1. Now everything in sight's integer valued and non-negative. Well, you can't have any of these happening unless b is 0, or you'd be too big. So the b's have to be 0. And then from here you can see, in fact, it's just plus or minus 1 that works. Okay, so we have a handle on the units. It's just plus or minus 1. Now, let's look at reducibility in this ring. So suppose z is reducible in the ring, so that means it can be factored as some u times v, where neither the u and the v are units. So saying that neither of the u and the v's are units would mean that their norms are not 1. Okay, well, if the norms aren't 1, that means they have to be bigger than 1 here, so what could they be? Neither of these are 0, because z is not 0. So, well, if you look at a squared plus 5b squared, the smallest that can be after 1 would be if a were 2 and you had no b's. So that would mean the norm would be 4. Well, if both of these are 4 as a minimum, then the norm of z has to be the product of norm of u, norm of v. So that would have to be at least 4 times 4 has to be 16 at least. So if something's reducible, it would have to have norm 16 or greater as a minimum. And of course, the units are where the norm is 1. So anything between 2 and 15 can't be reducible. All right. With this in hand, we can find 2 factorizations where everything is irreducible, and they're not the same. So look at these 4 elements, 2, 3, and 1 plus or minus I root 5. All of these norms are between 2 and 15. They're 4. They aren't units, and they're not reducible, so they're irreducible. Okay, well, here is the example. 6 in this ring can be written as 2 times 3. That is an irreducible decomposition of 6. And it can be written as 1 plus I root 5 times 1 minus I root 5, which is a separate and completely different and non-associative product of 6 into irreducibles. So in this ring, there's no way we can hope for unique factorization because it's just not true. Okay, this shows the type of problem you can have in the failure to be unique. It's easy and in some ways less interesting that sometimes you can't even factor things into irreducibles. But what we haven't defined so far at all is a precise definition of all this. So let's go ahead and get to that definition of what unique factorization should mean. All right, let's start with D, an integral domain. We'll say that D is a unique factorization domain, and everyone writes this as a UFD if for every R in D, of course, we throw out 0, so R is not equal to 0, and we throw out units. Each of these R's satisfies 2 conditions. First of all is the existence of the factorization. Every R is a product of irreducibles, so a product of some pi's, I equals 1 to n for some n. Okay? And the second part is uniqueness. If you write R as a product of some other possible irreducibles, some qi's, I equals 1 to m, then first of all, you have the same number of terms, n is equal to m. And second of all, you can re-index these, just change their order, so that the pi's and qi's are associates. In other words, that means they're just off by a unit, right? You can always take a factorization into irreducibles and stick a bunch of units, U inverse everywhere, and get something that looks a little bit different, but not actually being significantly different. Anyway, so that's existence and uniqueness, and that's what a unique factorization domain means. For examples, of course, The beginning of the class was the theorem that Z was a unique factorization domain. That was the fundamental theorem of arithmetic. And by the example we just did, Z attached the negative root of 5 is not a unique factorization domain. We didn't show it, but in fact it does satisfy 1. You can write everything as a product of irreducibles, but what we did show is that it definitely doesn't satisfy 2. There are just different irreducible factorizations for some elements. Okay, another definition here. Start with an integral domain, D, some P in D that is not 0. We say that an element P is prime if the ideal it generates is a prime ideal. So remember, what did prime ideal meant? It meant that whenever a product was in this ideal, so if AB is in the ideal generated by P, then either A or B was already there. Let me reinterpret this. All right, so being in the ideal generated by P just means P divides you. So I can rewrite this condition about being prime as saying, you're prime if and only if the following is true. Whenever P divides a product, that means P divided one of the terms already. So if P divides AB, P divides A, or P divides B. So we saw for prime numbers in the integers this was true. Okay, now just remember we also had previously the definition of irreducible. Irreducible meant the only divisors of something were units and associates. So for the integers, this was the original definition of prime. And it's easy to see for the integers, both the definition we're using here for irreducible and the definition we're using for prime are equivalent. But in general, these are just different. So irreducible means the only divisors are units and associatives. Saying an element is prime means that whenever that P divides a product, it divided one of the terms already. Okay? So writing down what we just said, for Z, irreducible, it turns out is the same concept as prime. So in general, we'll see soon that prime is actually stronger than irreducibility, and it always implies irreducibility. But if you're irreducible, you don't always get prime. And we've actually have an example of that already. For example, in Z attached the negative root 5, square root, we saw earlier that 1 plus I root 5 was irreducible. But I claim it's not actually prime. To see that, just kind of rehash part of that argument. We saw that 1 plus I root 5 divided 6, which is 2 times 3. And I claim that 1 plus I root 5 can't divide 2, and it can't divide 3, so it won't be prime. So anyway, you can read it in your book, but the norms don't match out. You would have to have the norm of 1 plus I root 5 dividing the norm of 2, and it doesn't. And similarly, it doesn't divide the norm of 3. So you just calculate those, and you see, therefore, it can't divide them. So prime, well, as I said, soon we'll see, is stronger than irreducibility. It always gives you irreducibility, but the reverse is not true. There are rings where they're the same, and those will be important. But anyway, so far, we just know they're different. Okay, let's prove this fact, that prime always implies irreducibility. Okay, start with something that's prime. Suppose that it can be written as a product. We want to show that it is irreducible, which means either A or B would have to be a unit. Well, since P is prime, it divides either A or B. Say it divides A. That means A can be written as PU, where U is a unit. We can then take this expression for A and substitute it back in here and get P is equal to... All right, so then you can cancel out the P's. So 1 is U times B, which means B is U inverse, which means B was a unit. So the only way you could factor P into two things is if one of them was a unit, and that meant that P was irreducible. So in general, prime always gives you irreducible, We've seen the reverse is false. The next lemma says that if you have a unique factorization domain, then you always get the reverse. Okay, so here's the lemma. Let D be a unique factorization domain. Part 1, prime is the same as irreducible in rings like this. All right. Part 2, if you have a bunch of distinct primes, pi, then the only divisors of some product of them, some product of powers of them, pi to the mi, are things of the form a u, where u is a unit, and then those prime elements to a power that's at most mi. Okay. All right, proof. First of all, we already know prime gives irreducible, so we just need the reverse, that irreducible gives prime. Well, let's start with something that is irreducible. We want to show it's prime, so suppose that it divides a product of two things, a, b. Well, that just means that AB is P times something. Let's call it PC for some C and D. All right, because we're in a unique factorization domain, then we can factor everything into irreducibles. So I can factor the A into a product of irreducibles, the B into a product of irreducibles, and the C into a product of irreducibles. So here it is. This is a product of irreducibles. That's A, that's B, and that's C. So the Pi, Qj, and the Rk's are irreducibles. But at this point, I have two things with the left-hand side is a product of irreducibles, and the right-hand side is a product of irreducibles. So by uniqueness, this P has to appear either in here or in here, at least up to a unit. Well, P or Q, suppose it's the P's. That means P is the same as some Pi naught times a unit, U. Well, of course, this means that P divides Pi naught, and since Pi naught is one of these terms here, that means, and this guy's A, that means P divides A, and that's it. All right, let's turn to part 2. All right, let's start with some A that's not 0 and not a unit. Write it as a product of irreducible powers, Pi to the mi. And suppose some B divides A. Of course, B isn't 0 here, and for B not a unit. Then we need to show the condition of the statement, so write B as its own factorization into irreducibles. So A is equal to B times C. Factor A, as we've already done here, as a product of irreducibles. Factor B here as a product of irreducibles, and C here. Now, we can re-index everything so that, again, the left side is a product of irreducibles, the right side is a product of irreducibles, so we can factor everything, so we can re-index everything so that we're using the same irreducibles. So re-index everything, so Pi is Qi is Ri. One technicality here is that, one of the primes in Pi might only appear in this term, but not in the R's. Well, in that case, we can still throw it in for free as long as we allow exponents to be 0. It'll just be that irreducible to the 0th power. So that way we can get all of them to have the same irreducibles. So then you just look at their powers. You get mi has to be ni plus li. And that gives the result because the li is at least 0. Okay, so that's that. To actually now get our big theorem, we're going to need more definitions. All right, start with an integral domain, as always in this section. A bunch of elements ai in the d's, 1 less than or equal to I up to n, and not all of them 0. We'll say that some element d in D is a greatest common divisor. So we'll write that as the GCD of A1 through AN if two properties hold. Number 1, the first is that D is a divisor. It's a common divisor, so it divides all the AIs. And if C is any other common divisor of all the AIs, then C divides D. Okay? So if you look back to our original definition of greatest common divisor back in integer land, we modified it after a few iterations, and this was the version that we came up with and the one that we used the most. And so this is the one that actually generalizes. Now, an important point here is this A is underlined because it turns out this is usually not unique. And so that means this expression here is a little ambiguous. So we'll see in a second, or I'll claim in a second at least, that you can always modify. It's unique up to multiplication by a unit. And so when you say D is the greatest common divisor, you really just mean you picked one of them, and you can get all the others by multiplying by a unit. So let me write that here. So here's the fact, and you'll check this in your homework. It's straightforward. If you have a greatest common divisor, then some D prime is a greatest common divisor as well, if and only if it's an associate of D. In other words, D times a unit. All right, continuing on with the definition. All right, just as back in integer land when the greatest common divisor was 1, and that was the only, remember we always picked the positive greatest common divisor, and so that was the only unit, was plus 1, the only positive one. So when the greatest common divisor is a unit, we say that A1 through AN are relatively prime. Now, of course, we saw in the integers that greatest common divisors always existed, and we always picked the positive one, so that made it unique. However, they don't always have to exist. For example, I claim there's no greatest common divisor of 6 and 2 plus, let me put a 2 there. There we go, 2 plus 2I root 5 in Z attached to the negative square root of 5. Now, the norm of the first is 36, and the norm of the second, you can check, is 24. And it's clear that if you have a common divisor of these two things, then the norm of the common divisor has to divide 36 and 24. So if that norm of C, a common divisor, divided 36 and 24, then that would mean the norm of C had to divide 12. But I claim there aren't elements in Z attached to the negative root 5 whose norms divide 12. Wait a second. No, what I really mean is that we can write down all the elements whose norms divide 12. And then we can check that none of those things are common divisors. So here's what you have to check. So here's the claim. Just mess around for a minute, you'll see that the only elements of Z attached to negative root 5 whose norms divide 12 are plus or minus 1, 2, and 1 plus I root 5. After that, then you just have to check that each of these fail to divide both of these numbers. Yeah, in this ring, of course. And as a result, you won't have a greatest common divisor. Okay, so existence may fail. That's what this example shows. One warning is this, that even when we have greatest common divisors, when they do exist, in the integer land, these were always linear combinations. Remember that ax plus by thing? That's not always true. It's usually not true, even when they exist. They don't have to be linear combinations of the a and b. There will be some nice cases where that's true, but not in general. All right, that's our first definition that we need, the notion of greatest common divisors. And then our second one is the following. All right, start with an integral domain. We say it satisfies the ascending chain condition on prime ideals. That's a mouthful, so let's write it as follows. The ACCP. Okay, ascending chain condition. If whenever you've got a bunch of AIs, so that the ideal generated by AI is contained in the ideal generated by AI sub plus 1, so a nested set of ideals possibly getting bigger and bigger and bigger, then there's a K so that, in fact, this chain stabilizes. All these ideals are the same after some point. Okay? That's the ascending chain condition. Let me reinterpret this in alternate language that's useful. It's clear that the ideal AI is contained in AI plus 1 if and only if AI is in the guy on the right, so if AI is an element of AI plus 1. So what does it mean to be in the ideal generated by AI plus 1? It means that AI plus 1 divides AI. So a nested increasing sequence of ideals here generated by a single element is the same as you have a sort of a greater and greater division of the higher AIs dividing all the lower A sub i's. Of course, we can do the same thing on the right side. So these two ideals are the same if and only if both generators divide each other, because that gives both of these inclusions, like over here. And we've already seen this is the same as saying that the A sub I and A sub I plus 1 are associated. So the chain stabilizes if and only if all these generators are the same up to a unit. All right, let's look at an example here. All right, if we have a unique factorization domain, then from that previous lemma, every element there that's not a unit or 0 has only a finite number of irreducible things that divide it. And if you, let me just say it this way, there are only finitely many divisors. We wrote them all down up to units. Therefore, the chains have to eventually stabilize because here, every time you add a divisor, I mean, you're using one of the divisors and you can only add a finite number of them up to units. So all the unique factorization domains satisfy this ascending chain property on principal ideals. For example, the integers. However, not everything satisfies this property. Consider D to be all the polynomials over Q of x, so that f of 0 is in z. So that's just the constant term, has to be an integer. All the other coefficients can be rational. Then you get an infinite, strictly increasing chain of principal ideals with this x contained in a half x, contained in a fourth x, eighth x, and so on. It's clear that each of these are contained in each other. For instance, the first inclusion, you have to show that 1 half x divides x, and it does. You just multiply by 2. You also want to show that they're not associates, so that the one on the right is strictly bigger. And that's easy because the only associates in here, in general, would be the constant ones, and the only constant ones that are invertible would be plus or minus 1. So anyway, that's an example that you don't always get this ACCP. All right, this leads us to our big theorem, which is kind of surprising that you can do this. Okay, here are the three conditions. For D in integral domain, the following are equivalent. 1, D is a UFD. 2, D satisfies the ascending chain condition on principal ideals, and all the irreducible elements are actually prime. In other words, irreducible is the same as prime in these rings. Or 3, D satisfies the ascending chain condition on principal ideals, and greatest common divisors always exist. So you can do UFD by any of these three. I'm just going to write the proof, I guess, for 1 and 2. You can look at how 3 fits into that. It's not really any harder. It's no new ideas, but it takes a lot of work, or a lot of writing rather, and I don't want to spend that much time. So we'll just prove the equivalence of 1 and 2 here, and you can look in the book for 3. All right, let's prove that 1 implies 2. All right, we've already done the work that UFDs always have the property that irreducible elements are prime, so that's done. We just need the ACCP. Suppose we have a chain of ideals that aren't 0 and not the whole ring. A1, A2, A3, all nested in each other. These are principal ideals. And of course, we're going to factor each of these A's using the unique factorization domain. All right, so each of these A's can be written as a product of irreducibles. And up to units and re-indexing, we can assume we're using the same irreducibles everywhere, as long as we allow this exponent to be 0. That way, if you don't use that irreducible, I mean, you can still have it in the list, but the value can be 0. Okay, now AI divides AI minus 1, which divides AI minus 2, all the way back to the beginning, divides A sub 1. So if you look back at the theorem about divisors and who divides who, then we get that all of these m's can't be growing. So all these m's, mi has to be less than or equal to mi minus 1, all the way up to less than or equal to 1. So there are only a finite number of times that each of these m's can dip down. And there are only a finite number of these m1s that are bigger than or equal to 0. So all together, all these m's can only drop at most a finite number of times. And after that, they have to stay fixed forever, wherever they are, which means that you have a constant set of ideals from that point on. Anyway, that gives you the stabilization. All right, so eventually past some k, all these m's have to be the same, so all the mi plus 1s are the previous mi. And once all the powers are constant, then they have the same irreducibles up to units, so all the ai's have to be the same up to a unit, which means the ideals have to be the same from that point on. So you get the ACCP. All right, let's go backwards. 2 implies 1. Now, number 1 is really both an existence and a uniqueness. So let's do the existence first. Okay, start out with A naught, an element of D, not 0, not a unit. We need to show it's a product of irreducibles. Okay, write D sub f for the set of elements of D that are a finite product of irreducibles. Then our goal is simply to show that A naught is actually in there. It's something that's a finite product of irreducibles. We'll argue by contradiction. So suppose A naught is not in DF. At the very least, it's not irreducible, or else, because irreducibles are in there, the product of one thing. Well, okay, it's not irreducible. What does that mean? It means it's a product of two things that are neither 0 nor units. So write A naught as A1 times B1. Now, if A1 and B1 were both in DF, then of course A naught would be as well, because you could write A1 as a finite product, B1 as a finite product, glue them together, A naught's a finite product, but it's not. So at least one of these, A1 and B1, one of them can't be in DF. Let's reindex and suppose it's A1. Okay, now we start repeating. A1, since it's not in DF, is not irreducible, so it factors into something that's not a unit and not 0. And then both of these can't be in DF. So one of them, say it's A2, is not in DF. All right, now you just keep doing this forever. You have the sequence of A's that splits into two things, and always there's something in there that's not in DF. And this gives you a chain of ideals. Like this, A naught contained in the ideal generated by A1, contained in A2, contained in A3, and that's because, for instance, A1 divides A naught, so you get this reverse inclusion of A naught contained in A1, and likewise. And it goes on forever, and even more importantly, these are strict inclusions. And that's because the only way they could be equal is if they were only, if for instance A naught and A1 were associates, if they were off by a unit. But the only way they could be off by a unit is if these B's were units, and part of this whole setup was that they weren't units. So these are all strict inclusions. And this would give a contradiction to the ascending chain property on principal ideals, and that's the contradiction we wanted. So we have existence. All right, let's do 2 implies 1, the uniqueness part. All right, for this we have to start out with something that has two possibly different factorizations into irreducibles. All right, start with A naught. The pj's are irreducible, the qj's are irreducible. What we want to show is that, of course, n is equal to m, and that after reindexing, actually all the pi's are the same as the qi's up to a unit, so that they're associates. So since the p1 is an irreducible, the assumption is that it's actually prime here. And then since it divides this product here, because it divides A naught, it actually has to divide one of these guys individually. So after reindexing, we might as well assume it divides Q1. Okay, well, since these guys are irreducible, you guys know already that if one irreducible divides the other, then they're the same up to a unit. So that's the first step. Q1 is in fact equal to U1 up to P1. And now you just keep repeating. You, in fact, can cancel out the first term from this one and the first term from this one. So now you've got less terms on both sides. And keep repeating. You can cancel the second ones after reindexing the third ones until you get all the way down to one of the sides being 1. And when that happens, the other side actually, since it's a product of irreducibles, that can only happen actually if I only had units left. So that will actually give the n is equal to m and equality up to units. But anyway, that's easy. All right, so that's the end of that proof there. All right, quite an impressive accomplishment that you can do this. Of course, it's a bit of a sham because checking this is usually hard. Scrolling back up here, you want to conclude something's a UFD, but checking the ACCP or that irreducibility includes prime or that GCDs exist, often that's difficult. But even though it's difficult, it's a very powerful result. So you got to pay somewhere, and this at least gives you a toehold, something to shoot for. And we will see in a number of examples that we can do this. All right, soon we're going to see that we get unique factorization domains kind of by straightforward techniques that we use a lot in 3 types of categories. The first will be that if we have a UFD, then the polynomial ring over that stays a UFD. And we're usually going to apply this when D is a field. Fields are automatically UFDs because vacuously there's nothing to check. They just have zeros and units, so done. So polynomial rings over fields will be UFDs. We'll also get them in a category called PIDs, the next section, principal ideal domains. And these are just domains, all of whose ideals are principal. And then the third category is Euclidean domains. These actually include principal ideal domains. Again, we'll do it in the next section. But these are essentially gadgets where there's some type of division algorithm. And whenever you have a type of division algorithm, then you're going to get a unique factorization domain. All right, one final note that you'll do in your homework. Suppose we're in a UFD and we take some element and factor it into primes or irreducibles, same thing, prime powers, and some other element into prime powers. If we allow the exponents to be 0, then we can use the same prime powers here as we do here. Then, just as in the integers, you get a formula for the greatest common divisor. And that is, it's the minimum of these 2 exponents. So just what you'd expect. All right, that's it for this section.